Salut tout le monde. Welcome back to another episode of me, Anthony, reading Differential Geometry by Erwin Kreisig out loud on screen for you guys. Last 2, 3, 4 episodes were all casting couch style, if you will. Not really, not true casting couch style, but I was just filming with my phone and a tripod on my couch instead of, here in front of the whole booktube style backdrop and all this, or, it's not like the green screen episodes I had. It's a little bit hard to film the green screen episodes, but we don't have to talk about that. But this is the finale, like I said. These are the last 7 sections of the book. It's the last topic or theme for the book as well, which is surfaces of constant Gaussian curvature, which at this point in the book, I'm feeling pretty confident in what you might call like my undergrad level classical differential geometry abilities. Namely, I talked about this in the last episode, but I took a look at this MIT OpenCourseware course for computational geometry, which, a lot of people say this about kind of like online resources in general. They'll be like, oh, there's so much out there online for free. You can just teach yourself whatever you want. But obviously, most people, from what I gather, just don't do that. It's kind of like a matter of like human will or the lack thereof. That's why people don't just, read from Wikipedia all day long instead of doom scrolling on something like Instagram or TikTok, right? There's a difference in the nature and the quality of the information. But those MIT OpenCourseware courses are really useful if you do go through them and if you do put in the work. So that computational geometry class I was talking about, that's a graduate level listing under the mechanical engineering department, but it's all like math and then computational, like implementing the numerical routines for the math that you go over, which is all, like splines, curves, surfaces, solid modeling, all that kind of stuff. I touched on this in the last episode. It was like the first homework assignment for that computational geometry class is basically a recap of just how can you use first and second fundamental forms? What does that mean? How do you interpret them? How do you use the Frenet equations? How do you, kind of in a rough sense, well, not exactly a rough sense, in a very detailed sense, it could turn out, you find the differential equations for maybe like principal curvature or lines of curvature, and then solve those, right? It's a different approach than kind of what I did in my filling in the gaps of Bernard Riemann's habilitation thesis, where it's like you start off with, these robust curvature tensors and you simplify or reduce them down through things like tensor contractions and whatnot to get, scalar Ricci curvature. And, you're putting these into these conformal differential equations at that point, and it's all this Louisville theorem stuff. So like that's a whole other take. This computational geometry homework is very much like the average problem in this differential geometry book, which is like, okay, identify the scenario in terms of like curves, surfaces, curves on surfaces, and plug and chug calculate the coefficients of the first and second fundamental form. And then it's like, okay, how are you going to use that? What does this mean? That kind of stuff. Can you draw pictures based upon these interpretations, right? So, yeah, there's the two applications of differential geometry. There's, on the one hand, general relativity. On the other hand, there's like CAD, computer-assisted design, CAM, computer-assisted manufacturing, CAD, CAM stuff, and then going into the pathway down computer graphics, way more marketable in like a capitalist like engineering job sense of things, but then like general relativity stuff is like way cooler from like the fantasies that drive people to become scientists and engineers in the first place, you know what I mean? Anyways, this is the finale. I figured I would give a little rant at the beginning before we start. Section 90, surfaces of constant Gaussian curvature. Surfaces of constant Gaussian curvature, capital K non-zero, are of great interest since the intrinsic geometry of these surfaces exhibits properties similar to that of the plane. We will later prove that this intrinsic geometry is locally identical with the so-called non-Euclidean geometry, which has been developed from quite another point of view, which we will see in the very last section, section 96. We first consider the surfaces of constant Gaussian curvature in general. We introduce geodesic polar coordinates, u1, u2, where the 1 and the 2 are superscripts, in this case, on the surface capital S under consideration. Depending on capital S, these coordinates may be valid on the entire surface or on a portion of S only. Then the first fundamental form is given by expression 52.1. This is just the geodesic variation of the first fundamental form. ds squared equals du1 squared plus g sub 22 in terms of u1 and u2, and then times du2 squared, where g sub 22 in terms of u1 being equal to 0, and then u2 still being a free variable, then this g sub 22 is equal to 0, and the partial with respect to u1 of the square root of g sub 22 evaluated at u1 equal to 0 is equal to 1, for which we can refer back to expression 53.1 in section 53, which states that the limit of u1, that the limit as u1 approaches 0 of g sub 22 equals 0, and that the limit as u1 approaches 0 of partial with respect to u1 of the square root of g sub 22 is also equal to 1. Furthermore, by 52.2, which is a formula for Gaussian curvature, capital K equals negative 1 over the square root of g sub 22, then times partial squared, or I guess you could say a second derivative with respect to u1 of the square root of g sub 22 is calculated to be equal to the fraction of 1 over the denominator of 4 times the square of g sub 22. And then that fraction is then times the square of partial g sub 22 partial u1. And then that is all minus 1 over 2 times g sub 22, then times partial squared g sub 22 partial u1 squared. So by this, we have that capital K, returning back to section 90, is equal to negative 1 over the square root of g sub 22, then times partial squared of the square root of g sub 22 partial u1 squared. This is a linear differential equation of second order, which can be written in the form partial squared capital B partial u1 squared plus the Gaussian curvature capital K times capital B equals 0, where capital B here denotes the square root of g sub 22, which is really equal to the square root of lowercase g, where this denotes the discriminant of the first fundamental form, which is really calculates out to g sub 11 times g sub 22, then minus the square of g sub 12, where what those really mean are, of course, g sub 11, 12, 22, those are all coefficients of the first fundamental form, which represent dot products of tangent vectors along, let's say, the first or second direction. So g sub 11 would be take the derivative along direction 1 and then scalar product that with itself. Looking at the inner product space of these coefficients and these, different, basically what it comes down to is like if you're on a surface, you've got tangents, you've got normal vectors, and you can do tangents, scalar product with tangents. That's the first fundamental form. Tangents, scalar product with normals, that's the second fundamental form. Normals, scalar product with normals, in a way, that's the third fundamental form. Really, the way to think of that is more of like projecting onto a unit sphere and all this, but like I said, it's really more about the first and second fundamental forms than those inner product spaces. Anyways, we consider the solutions of this equation for constant Gaussian curvature capital K. The first case is that if capital K is equal to 0, the solution of the above linear differential equation of second order is capital B equals capital C sub 1 of u2, then times u1, plus capital C sub 2 in terms of u2. from the expression at the beginning of this section, we have that capital C sub 1 equals 1 and capital C sub 2 equals 0. Hence, in this case, ds squared equals du1 squared plus u1 squared then times du2 squared. And again, this is when the Gaussian curvature capital K is equal to 0, as it must be for polar coordinates in the plane. If K is greater than 0, then capital B is equal to C1 of U2 then times the cosine of square root of K then times U1, still within the cosine, but then outside the cosine we have plus C2 of U2 then times the sine of square root of K U1. And that is the solution of our, let's say, governing linear second order differential equation that we're talking about here. In consequence of the expression for g sub 2 2 when u1 is equal to 0 and we have free u2, in consequence of that we have that c1 equals 0 and c2 equals 1 over the square root of k. Therefore, g sub 2 2 equals capital B squared, which equals 1 over k then times sine squared of the square root of k then times u1. And ds squared equals du1 squared plus 1 over k then times sine squared of square root of k then times u1, and then that is times du2 squared. Again, this is for positive Gaussian curvature. In the case of negative constant Gaussian curvature, capital K is less than 0, the solution of our governing linear differential equation of order 2 takes the form capital B equals C1 of U2 then times the hyperbolic cosine of the square root of negative capital K then times U1. This is the argument of the hyperbolic cosine. But then, outside of it, we then have plus C2 in terms of U2, then times hyperbolic sine with an argument of square root of negative K, and then times U1 to close off the argument. Where the hyperbolic functions are defined as follows, which is the conventional definition from what it looks like at a glance, obviously. Hyperbolic cosine equals cosine with an argument of I times x, which is equal to, you could say, the average of e to the x and e to the negative x. So we have 1/2 times the quantity e to the x plus e to the negative x. And then similarly, thinking about how sines, cosines are traditionally, conventionally defined, where we have, orthogonality and derivatives and phase offsets of pi over 2 and all that kind of stuff. Similarly, to keep with how we define hyperbolic cosine, you have hyperbolic sine is negative I times sine with an argument of I times x, which calculates out to be 1/2 times the quantity of e to the x minus e to the negative x closed quantity, as is well known. Everybody here watching this video on this channel, that should be true. You should just already know that. You know what I'm saying? In consequence of that g sub 2 2 relation from the beginning of this section, we have that c1 equals 0 and c2 equals 1 over the square root of negative k. Hence, ds squared equals du1 squared plus 1 over negative k, then times the square of the hyperbolic sine of argument square root of negative k, then times u1. The u1 is not under a square root. That closes off the argument of the square of the hyperbolic sine, and then we have du2 squared. And this is, once again, where k is less than 0. And for this, we can refer to a reference by HSM Coxeter, and this was also referred to in section 15.5, it says here. I'm not going to hunt this down right now, but we're going to move on. Planes and spheres are simple examples of surfaces of constant Gaussian curvature, k equals 0 and k greater than 0, respectively. Examples of surfaces of negative constant Gaussian curvature will be considered in the upcoming section 93. We come to one of the last problems in the book. This is problem 90.1, and I will just say that the next time after this that there are any problems, it's the problems at the end of the last section. So after I read the solution to this problem, the next time that I will be reading from the solutions at the end of the book will be the end of the book. So anyways, problem 90.1, introduce coordinates on a sphere so that the first fundamental form is given by expression 90.4 above. That's the, first fundamental formulation for positive constant Gaussian curvature. And it's kind of like all of the terminology is converging together. It's like saying positive constant Gaussian curvature and being like, oh, we're on a sphere. That's like all of these things are all ways of saying basically the same thing, right? So this problem is just like, we're just rounding this all out. The solution of problem 90.1, the representation, which is a vector x in terms of u1 and u2, which is equal to 3 entries, entry-wise given by, first, r times the cosine of u2, then times the sine of u1 over r, and then we have the next entry being r times the sine of u2, then times the sine of u1 over r, and then in the third and final entry we have r times the cosine of u1 over r. This representation is of the desired type. The quote north pole unquote capital P corresponds to u1 equal to 0, and the quote equator unquote corresponds to u1 equal to 1/2 pi times r. The north pole capital P is the center of these geodesic polar coordinates. Namely, we have that g sub 1 equals 1, we have that g sub 1 2 equals 0, g sub 2 2 equals r squared times sine squared of u1 over r, and ds squared equals du1 squared plus r squared times sine squared of u1 over r, then times du2 squared. And since capital K equals 1 over r squared, this is in agreement with the g sub 2 2 where u1 is equal to 0 and u2 is a free variable relation, expression 90.4 from the main section. Moving right along, section 91, isometric mapping of surfaces of constant Gaussian curvature. The concept of isometric mapping and related concepts were introduced in section 57. The Gaussian curvature K is an invariant under isometric mapping, for which we can refer back to theorem 57.2, which, as a refresher, states isometric surfaces have the same Gaussian curvature at corresponding points. Corresponding curves on those surfaces have the same geodesic curvature at corresponding points. Hence, at corresponding points of two isometric surfaces, the Gaussian curvature must necessarily be the same. However, in general, this condition is not sufficient, as can be seen from the following. Example from Stackel and Wangerin. If the logarithmic curve x sub 3 equals the log of x sub 1 is rotated about the x3 axis, it generates a surface of revolution which can be represented in the form of a vector x in terms of u1 and u2, which is equal to, entry-wise, u1 times cosine of u2, then next u1 times sine of u2, and then next the logarithm of u1, where u1 in all of these is greater than 0. The corresponding first fundamental form is given by the expression ds squared equals the quantity 1 plus a fraction 1 over the denominator u1 squared, closed quantity, then times du1 squared, plus u1 squared, then times du2 squared. This surface has the Gaussian curvature K equals -1 over a denominator of the quantity 1 plus u1 squared closed quantity squared. The right helicoid, which we went over in the previous section 81, can be represented in the form vector x in terms of u1 star and u2 star equal to 3 entries, the first being u1 star then times cosine of u2 star, and then second we have u1 star then times sine of u2 star, and then third and finally we have u2 star. To this representation there corresponds the first fundamental form ds star squared equals du1 star squared plus the quantity 1 plus u1 star squared closed quantity then times du2 star squared. And the surface has the Gaussian curvature K star equal to -1 over the denominator of the quantity 1 plus u1 star squared closed quantity squared. The mapping given by u alpha star equal to u alpha, where alpha is equal to 1 or 2, is such that at corresponding points the Gaussian curvature of both surfaces is the same. But this mapping is not isometric, for which we can refer back to theorem 57.1, which, to remind ourselves, states that an allowable mapping of a portion S of a surface onto a portion S star of a surface is isometric if and only if at corresponding points of S and S star, when referred to the same coordinate systems on S and S star, for which we can refer back to section 56, The coefficients of the first fundamental forms on S and S star are the same. So G sub alpha beta equals G star sub alpha beta for all alpha and beta, which are just equal to 1 or 2. So we will prove that there does not exist an isometric mapping of one of those surfaces onto the other. In consequence of the above relations earlier in this section, 91.2 and 91.4, the most general mapping under which the Gaussian curvature at corresponding points is the same must satisfy the condition 1 plus u1 star squared equals plus or minus the quantity 1 plus u1 squared. Hence, either u1 star squared is equal to positive or minus u1, or u1 star is equal to the square root of negative 2 minus u1 squared. So either of those must be true, while u2 star can be an arbitrary function of u1 and u2 such that its first partial derivative with respect to u2 does not vanish. Namely, u2 star is equal to phi in terms of u1 and u2, and phi sub 2 is non-zero, where phi sub alpha is equal to partial phi partial u alpha. So by inserting some of these previous relations into each other, namely 91.5a and 91.6 into 91.3, we obtain ds star squared is equal to du1 squared plus the quantity 1 plus u1 squared closed quantity, then times a new quantity phi 1 times du1 plus phi 2 times du2 closed quantity squared. In order that this expression should be identical with, from the very beginning of this section, this initial ds squared first fundamental form expression, it's like the first fundamental form. That doesn't make sense. Anyways, in order that this expression should be identical with that one towards the beginning of this section, then the conditions first, where we have 1 plus a quantity, 1 plus u1 squared closed quantity, then times phi 1 squared. This is equal to 1 plus 1 over u1 squared. That's the first condition. Second condition, phi 1 times phi 2 is equal to 0. Then the third condition, quantity 1 plus u1 squared closed quantity, then times phi 2 squared is equal to u1 squared. These three conditions, in order for our identical first fundamental forms goal to be achieved, those conditions should be satisfied. So from these expressions that we've been working out so far, we have that phi 1 is equal to 0. Applying this relation to the first of the three conditions that I just mentioned, we obtain a contradiction. If we insert another one of our earlier expressions, 91.5b and 91.6, which is still on screen, into 91.3, we find ds star squared is equal to the fraction negative of u1 squared over a denominator of 2 plus u1 squared, then times du1 squared, minus the quantity 1 plus u1 squared closed quantity, then times another quantity phi 1 times du1 plus phi 2 times du2 closed quantity squared. In order that this expression should be identical with, again, the initial first fundamental form in this section, the relations, first where we have a fraction negative of u1 squared in the numerator and then a denominator of 2 plus u1 squared, that fraction is then minus quantity 1 plus u1 squared closed quantity, then times phi 1 squared, which equals 1 plus 1 over u1 squared. Second relation, we have phi 1 times phi 2 equals 0, and the third relation is the negative 1 times quantity 1 plus u1 squared closed quantity, then times phi 2 squared equals u1 squared. It's a third relation. All of those should hold. So in this case, we also obtain a contradiction. Surfaces of constant Gaussian curvature k have the important property that if k is equal, the surfaces are isometric. In the case k equals 0, this fact has already been stated, which is theorem 59.3. Indeed, to remind ourselves, that states a sufficiently small portion of a surface of class r greater than or equal to 3 can be mapped isometrically into a plane if and only if it is a portion of a developable surface. In the other two cases, k greater than 0 and k less than 0, is an immediate consequence of expression 90.4 and 90.5 in the previous section. The coefficients of those fundamental forms are completely determined by the Gaussian curvature K. Hence, if two surfaces have the same constant curvature K, the first fundamental forms are also the same. In consequence of the fact that the expressions 90.3 through 90.5 were obtained by using geodesic coordinates, which in general are allowable on a certain portion of a surface, we may formulate our result as follows. This is from Ferdinand Minding, one of the, I guess, he was at the forefront of doing, you could say, like Riemannian geometry work in like the early 1900s, it seems like. Anyways, Theorem 91.1 by Minding. Two sufficiently small portions of surfaces of class r greater than or equal to 3 having the same constant Gaussian curvature are isometric. And now the last one I'm going to read for today, section 92, spherical surfaces of revolution. A surface of positive constant Gaussian curvature is called a spherical surface. A surface of negative constant Gaussian curvature is called a pseudospherical surface, or also hyperbolic if I'm not mistaken. In this and the following section, we shall consider spherical and pseudospherical surfaces of revolution. In consequence of Theorem 91.1, the intrinsic geometry of surfaces of the same constant Gaussian curvature is locally identical. However, the geometric form of these surfaces, as viewed from the embedding space, may be different, as we will now see. We start from a representation of a surface S of revolution of the form vector x in terms of u1 over bar and u2 over bar, which is equal to u1 over bar times cosine of u2 over bar, and then next entry u1 over bar times sine of u2 over bar, and then next entry we have function h in terms of u1 over bar. The corresponding first fundamental form is given by the expression partial squared capital B partial u1 squared plus capital B over lowercase c squared is equal to 0, where a prime denotes the derivative with respect to u rho over bar 1. What? Okay, what's on screen is bad PDF quality, where it says what looks like u over bar, and then there's a superscript rho, and then over that is a superscript, like a footnote of a 1. Really, that should just be u over bar 1. Anyways, we now introduce geodesic parallel coordinates u1 and u2 on S, so that the first fundamental form becomes ds squared equals du1 squared plus g sub 2 in terms of u1 and u2, then times du2 squared, for which we can refer back to 52.1, which is it is exactly what I just read. So, and the coordinate curve u1 equal to 0 is a geodesic. Then the curves where u2 is a constant are geodesics orthogonal to the curve where u1 equals 0, and the curves where u1 equal to a constant are geodesic parallels of the curve where u1 equals 0. We set Gaussian curvature capital K equal to 1 over lowercase c squared equal to a constant, and the square root of g sub 2 equal to capital B. Then the differential equation from section 90 takes the form partial square of capital B partial u1 squared plus capital B over lowercase c squared equals 0. Since lowercase c is a constant, then the differential equation I just read has the solution square root of g sub 2 equals capital B, which equals capital C sub 1 in terms of u2, then times cosine of u1 over lowercase c, and then we have plus capital C sub 2 in terms of u2, then times the sine of u1 over lowercase c. Since the geodesic curvature of the curve u1 equals 0 vanishes identically, we obtain from 49.9a, which, to recap, we're going to take quantity kappa sub g closed quantity and then an additional subscript which says u1 is equal to a constant where we're evaluating this. This geodesic curvature is equal to a fraction where we have 1 over a denominator of 2g sub 2 then times the square root of g sub 1, and that fraction is then times partial g sub 2 partial u1, which this calculates out to be 1 over the square root of g sub 1 then times partial in terms of u1 of the logarithm of the square root of g sub 2. That's 49.9a. So we obtain from that partial capital B partial u1 evaluated at u1 equal to 0 is equal to 0, and therefore capital C sub 2 is equal to 0. If u2 is chosen proportional to the arc length sigma of the curve u1 equal to 0, that is u2 equals sigma over lambda, then the first fundamental form becomes ds squared equals du1 squared plus lambda squared times cosine squared of u1 over lowercase c, then times du2 squared, where lambda is a constant, not 0. And the previous relations for fundamental forms from this section become identical if quantity 1 plus h prime squared closed quantity, then times d u1 over bar squared equals du1 squared, and u1 over bar equals lambda times cosine of u1 over lowercase c, and u2 over bar equals u2. From this, it follows that lowercase h prime equals the square root of entirely the quantity du1 du over bar 1 squared minus 1, and du1 over bar du1 equals negative lambda over lowercase c, then times the sine of u1 over lowercase c. Hence, altogether, x3 equals the integral of an integrand, which is the square root of entirely 1 minus lambda squared over lowercase c squared, then times sine squared of u1 over lowercase c, closed quantity. So that's what the square root is. That's all the integral is integrating, so to speak. That's in terms of du1. So if lambda does not equal lowercase c, this integral is elliptic. And its function values can be found in the book Tables of Functions by E. Janke and M.D. And that was published in 1945. That definitely gives away the age of this book. I've remarked on that a few times because that reference has come up a few times in this book. I might even at one point towards the end of this just like open up the PDF I have of that book and then just demonstrate how anything that's tabulated in that book can be easily acquired with free, modern, open, like tools. You could just like, run basically it's like a glorified calculator that you could just like run from your terminals. Surely someone has published out there where you don't have to buy MATLAB, Mathematica, whatever. It's like you can get any calculation function value from that book for free using a computer today in 2025. Anyways, the surface of revolution under consideration is now represented in the form vector x in terms of u1 and u2 is equal to, entry-wise, first entry, lambda times cosine of u1 over lowercase c, then times cosine of u2, and then the second entry is lambda times cosine of u1 over lowercase c, then times the sine of u2. Then the third entry is the integral of the square root of 1 minus lambda squared over lowercase c squared, then times sine squared of u1 over lowercase c closed quantity, then du1, where in all of this, lowercase c is equal to 1 over the square root of capital K, and capital K is positive, non-zero, and lambda is also positive, non-zero, where in all of this, for the surface of revolution under consideration, u1 and u2 are the above geodesic parallel coordinates. In order that K is greater than 0, the meridians of the surface must be of such a form that their unit principal normal vector when bound at a point of the meridian is directed towards. In order that K is greater than 0, the meridians of the surface must be of such a form that their unit principal normal vector when bound at a point of the meridian is directed towards the axis of revolution. We obtain 3 different types of spherical surfaces of revolution corresponding to the values lambda equals lowercase c, lambda is greater than lowercase c, and lambda is less than lowercase c, respectively. So first, if lambda equals lowercase c, then our above representation for our surface of revolution takes the form vector x in terms of u1 and u2 is equal to, in the first entry, lowercase c times cosine of u1 over lowercase c, then times the cosine of u2, and then in the second entry, lowercase c times the cosine of u1 over lowercase c, then times sine of u2, and then in the third and final entry, lowercase c times the sine of u1 over lowercase c. This is a representation of a sphere of radius lowercase c with center at the origin of the coordinate system in space. Second case, if in our representation of our surface of revolution, lambda is greater than lowercase c, we obtain a surface which is called a hyperbolic spherical surface of revolution. I think nowadays we just call it a hyperbolic surface of revolution, but correct me if I'm wrong in the comments. And for a depiction of these so-called hyperbolic spherical surfaces of revolution, we can refer to figure 95a above. In this case, x3 is a periodic function. The surface consists of a succession of congruent portions called zones, each of which is bounded by 2 circles parallel to the x1, x2 plane. The coordinate u over bar 1, that's not a u and then superscript of a -1, that's another bad PDF moment here. It really should be u1 over bar. That coordinate is the radius of the circles parallel to the x1, x2 plane. From 92.5, which are the identical conditions above, we have that u over bar 1 is less than or equal to lambda. In order that x3 be real, we must have that the sine squared of u1 over lowercase c is less than or equal to lowercase c squared over lambda squared in our integral, which is in the third entry of our representation of these surfaces of revolution. So, by our, let's say, we'll call them our isometry conditions, we obtain from this that u1 over bar is greater than or equal to the square root of the quantity lambda squared minus lowercase c squared closed quantity. Hence, u1 over bar is equal to the square root of lambda squared minus c squared is the radius of the above circles by which every zone is bounded. The maximum value where u1 over bar is equal to lambda corresponds to the circle in the middle of every zone. And the third and final case, if we have that lambda is less than lowercase c, we obtain a surface which is called an elliptic spherical surface of revolution. Probably just called elliptic, but I could be wrong. In this case, the radii of the circles parallel to the x1, x2 plane can have every value of u1 over bar between 0 and lambda. x3 is again a periodic function. Each zone of the surface is now bounded by 2 points, and that was shown in figure 95 on the previous page of the PDF. We finally mention the isometric mappings of spherical surfaces into each other, referring back to theorems 57.1 and 91.1. Let S1 and S2 be two such surfaces having the same constant Gaussian curvature corresponding to values lambda equal to lambda 1 and lambda 2 respectively. The first fundamental forms are, first in the case for surface S1, we have ds squared is equal to du1 squared plus lambda 1 squared times cosine squared of u1 over lowercase c then times du2 squared, and for the surface S2 we have ds star squared equals du1 star squared plus lambda 2 squared then times cosine squared of u1 star over lowercase c then times du2 star squared. Now, setting du1 star equal to du1 and lambda 2 times du2 star equal to lambda 1 times du2, these two expressions become identical. Hence, the isometric mapping of S1 into S2 is given by the formulae u1 star is equal to u1 and u2 star is equal to lambda 1 over lambda 2 times u2. The image of the portion of S1 consisting of all points with coordinates u1 and u2 where u1 is greater than or equal to a, but also less than or equal to b, and we also have that u2 is greater than or equal to 0, but also less than, but not equal to 2 pi, consists of all points of S2 with coordinates u1 star and u2 star, and we also have u1 star is greater than or equal to a, but also less than or equal to b, and similarly, u2 star is greater than or equal to 0, but less than, not equal to 2 pi times lambda 1 over lambda 2. Consequently, if lambda 1 is greater than lambda 2, certain points of S2 correspond to several points of S1. If, however, lambda 1 is less than lambda 2, then the portion of S2 defined by u1 star greater than or equal to a, as well as being less than or equal to b, and u2 star being greater than or equal to 0, as well as less than but not equal to 2 pi, also contains points which are not points of the image of the above portion of S1. Under this mapping, meridians correspond to meridians as follows from the above relation 92.10, or these formulae here. And that's it for today. That's sections 90, 91, 92. Today I've got the red-violet foulard tie with the gray pinstripe suit, going with the, it's actually, it looks like they're black pinstripes, but they're really blue pinstripes on the white shirt. The gold tank watch, black leather, one hand. Then we got the Married to Myself gold variation, the thin ring. I call this outfit Poppy. It's inspired by 1989 George H.W. Bush. So, yeah, see you guys in the next one. Peace.